Let us discuss another aspect of double integrals. We know that when there are two variables in the integrand and we differentiate with respect to the two variables, we call such an integral as a double integral. Integrals may be in terms of the Cartesian coordinate or in terms of polar coordinate or another coordinate. Let us think of or let us discuss what is meant by change of variables. Let an integral be given in terms of two variables x and y. We want to convert it to polar coordinate. Why shall we think of converting? Earlier we have seen that when we consider a circle having its center on the x-axis and passing through origin, or when you have got a circle on the y-axis with the center on the y-axis passing through origin, in such cases, or even in the case of a circle or cardioid, we notice that polar coordinates will be a better choice. This is what we are going to emphasize. So, change of variables. Why shall we think of change of variables? Sometimes a new set of variables makes a problem simple. That means evaluation of the integral also may become simple. Let us see how to convert from a coordinate system x comma y to another coordinate system u comma v. Let x be a function of u comma v, y be a function of u comma v. Then in the integral or in the integrand, we replace x by that function of u comma v, y by the function of u comma v, and then the product of the differentials dx dy by j du dv. What is j here? Jacobian of xy with respect to u comma v. That is dou xy by dou u comma v. We know the meaning of the Jacobian. It is actually the determinant with elements row wise dou x by dou u, dou x by dou v, dou y by dou u, dou y by dou v. Let us now see how to convert from Cartesian coordinates to polar coordinates. X, y are the Cartesian coordinates, r comma theta are the polar coordinates. We know the relation between the two sets of variables. X is equal to r cos theta, y is equal to r sin theta. Jacobian here, that means dou xy by dou r comma theta is r. Therefore, in the integral, we replace x by r cos theta, y by r sin theta, and dx dy by r dr d theta. Then, of course, we have to write appropriate limits for r and theta. Let us discuss a couple of problems based on this particular aspect. The first problem on change of variables. The problem is like this. Evaluate by changing to polar coordinates the integral x is equal to 0 to 2a, integral y is equal to 0 to root of 2ax minus x square of x square plus y square dy dx. If we observe carefully, the limits here denote the part of the circle of radius a with the center at a comma 0 lying in the first quadrant. So in polar coordinates, the circle can be described easily. So here, by changing to polar coordinates, we'll be evaluating the integral. Here, the circle is described by r is equal to 2a cos theta. So the limits for r will be 0 and 2a cos theta. Limits for theta will be 0 and pi by 2. So in the integral, we replace x by r cos theta, y by r sin theta, x square plus y square by r square, and dx dy by r dr d theta. So given integral now becomes integral theta is equal to 0 to pi by 2 integral r is equal to 0 to 2a cos theta of r square into r dr d theta. Or it can be initially integrated with respect to r to get integral theta is equal to 0 to pi by 2 r to the power 4 by 4 to be evaluated at r is equal to 0 and 2a cos theta. Substituting the limit, we get 16 a to the power 4 by 4 integral theta is equal to 0 to pi by 2 cos theta to the power 4 d theta. Now cos theta to the power 4 can be written as 1 plus cos 2 theta by 2 whole square, because we know that cos square theta is 1 plus cos 2 theta by 2. So whole square we are writing. So the integral becomes 4 a to the power 4 multiplied by integral theta is equal to 0 to pi by 2 1 plus cos 2 theta by 2 whole square d theta. Expanding this, we get a to the power 4 into integral theta is equal to 0 to pi by 2 1 plus 2 cos 2 theta plus cos square 2 theta d theta. On integration again, cos square 2 theta is written as 1 plus cos 4 theta by 2. So integrating this, we get the sine function sine 2 theta, sine 4 theta, which vanish at both the limits. Therefore, on simplification, we get 3 pi a to the power. Let's discuss another problem. By using the transformation x plus y is equal to u, y is equal to uv, show that integral x is equal to 0 to 1, y is equal to 0 to 1 minus x, e power y by x plus y dy dx is equal to half of e minus 1. Here, two new variables u and v are given. X and y are given in terms of u and v. Let us try to observe that x is equal to u minus uv, y is equal to uv. That means expressions for both x and y are available. X we have rewritten, please note that x is equal to u minus uv, y is equal to uv. We can as well determine the Jacobian now, that is dou xy by dou uv, or determinant dou x by dou u, dou x by dou v in the first row, second row dou y by dou u, dou y by dou v. That becomes the determinant with elements 1 minus v minus u in the first line, second row v and u. So on simplification, it becomes u. That means in the given integral, we replace x by u minus uv, y by uv, x plus y by u, dx dy by j du dv or u du dv. The limit in terms of u and v can be observed from the inequalities representing the region 0 less than or equal to u less than or equal to 1, 0 less than or equal to v less than or equal to 1, or the given integral becomes integral v is equal to 0 to 1, integral u is equal to 0 to 1, e power uv by u, u du dv, or it becomes integral v is equal to 0 to 1, integral u is equal to 0 to 1, e power v into u du dv. Initially, we integrate with respect to u to get integral v is equal to 0 to 1 e power v into u square by 2 to be evaluated at u is equal to 0 and 1, of course followed by dv. Substituting the limit, we get half of integral v is equal to 0 to 1 e power v dv, or on integration you get half of e power v evaluated at 0 and 1, or it becomes half of e minus 1.